So I have the pleasure and honor to introduce my colleague, Eric Verschuur. Eric is a professor in the Department of Physics. Eric received his Master of Science degree in '86 and his PhD with honors in '91 from TU Delft, both in applied physics. After 5 years of research fellowship in '97, he became assistant professor, and since '99 he is associate professor at TU Delft at the Laboratory of Acoustical Wave Field Imaging within the M-Physics department. Since 2016, he is the program director of the Delphi Research Consortium, which is sponsored by 29 companies from the oil and gas industry, within which research is carried in the area of geoimaging. His main interests are wave field modeling, data processing, imaging, and inversion techniques. In '97, he received SEG's J. Clarence Carker Award, and in 2006, he was awarded with the Virgil Kaufman Gold Medal from the SEG. He has been selected as the EAGE European Association for Geoscientists lecturer for the Education Tour 2006 with a one-day course on multiple removal. He has been co-promoter of more than 20 successfully completed PhD candidates and many, many others as well. Thank you very much, Eric, for kindly accepting our invitation to train us on monitoring. That was actually the topic that was discussed in Suzanne Hank's discussion just last time. I hope that you have heard that imaging thing. So we are very much looking forward to your lecture. Thanks very much.
Good, thanks, Hadi. So it's my, it's my pleasure to be here and to present on this summer school. At the same time, Hadi also presented his work in our consortium meeting. So we are happy to contribute to each other and also not stay at that level, but try to work together and collaborate. That's our plan, and that's also how I will end my presentation today. So this is about monitoring, things we have been doing in our consortium. So let me see if this works. No, okay, we'll do it by hand. Okay, good. So this is the outline. So I will first say something about our consortium that Hadi already mentioned, and something about seismic imaging in general, because that's the tool that I'm going to show mostly. And then say something about that tool, without going too much into physics, because that is probably not the idea of such a multidisciplinary summer school. And then show you some things we have been doing. Of course, we have not been doing monitoring of hydrogen storage areas yet, because we would like to get into that field, and that will be part of the outlook then. Good, so what about the Delphi Consortium and about seismic imaging? So this is basically a simulation of a seismic wave, an acoustic wave that travels into the subsurface and gets reflected. And you see already, if you have a complex subsurface, it gets really a complex scattered wave field. And the idea is that by measuring these responses, we can create an accurate image of the subsurface, and even more, get more information about the actual parameters. So this is as opposed to the movies that Hadi always shows about a flow of material. So this is another kind of movement inside the Earth at a smaller scale, a smaller time scale. Anyway, so these are those wave fields, and when you measure them at the surface by geophones or hydrophones, depending on whether you are on or offshore, you get those nice acoustic responses, and then comes wave theory. And then you can basically backpropagate all that information and map it to where it came from. And then you can create such an image. And this is actually a very simple image. This is an image I created when I was a PhD student. So this image is already like 40 years old or 35 years old. 30 years old, maybe I have to be modest here. But this is more what they would look like in practice. So these are 3D seismic images with interpreted horizons. And in this case, this is an area where there are salt plumes. So very relevant of this workshop. And of course, in the old application, we are typically using this image to look what is below the salt, because that's where the reservoir typically could be of oil and gas. But nowadays we are going to would like to see, okay, what is happening inside the salt there, and how things are stored there. So I'm also very excited of this new application. At least for me, it's new. So what's about this Delphi consortium? So it has been around for a long time, actually since 1983. So actually I was doing my master's at that time. I just started to do my master's. I came there only in the 1986 when I finished my master as a PhD student. But so the aim is to use well, geophysical measurements, mostly seismic, especially at that time, and develop algorithms and imaging techniques to image and characterize the subsurface, basically. And it's a sponsored consortium by industry parties. And it's a kind of yearly automatically renewable until you basically stop sponsoring. So in this way, we can continue this well, the consortium for many years, and we have been doing that. So almost 40 years already of this kind of consortium research. And of course, what is the payback for the companies is to get the results, the software, the reports, etc. And also visit our meetings that we have twice a year. And if you want to see what are the sponsors, you can look at our website that I just showed before. And well, this is an overview of our current sponsors. You can clearly see these are typical sponsors of the, well, what we used to call oil and gas industry. So the big oil and gas companies, international, national, but also big contractors and also some smaller contractors. But all these companies are now also in a change. So they have renamed themselves into energy companies. And they're also now expanding their portfolio. And so we are in our research, of course. Well, by the money they bring in, we can pay about 12 researchers, PhDs and postdocs. And all those people also need supervision. So you see here a lot of faces of people that are involved in supervision of our current PhDs and postdocs. Well, we'll not go through all of them. Mostly are from TU Delft. But just to show you the size of the consortium. So if the whole team is together, we are with like 25 people. Okay, so that's kind of the background information. So what about this seismic imaging? Well, it is old, of course. It started already in the 70s, even before that. Our Groningen and gas field was discovered based on seismic images, a very premature type of imaging, but still, they found it. But since then has been a lot of developments. And one of the developments that we're doing ourselves in the consortium is to make sure that we use all of the seismic waves. So the seismic wave is a very complicated scattered wave field. And what we would like to do is to model that as accurately as possible. And we do that based on the actual outcome of the imaging. So we have an imaging process that produces, in principle, it produces an image, a reflectivity image, as you see on the top right, but it also produces a background velocity model. The propagation velocity model is required to do the imaging properly. They are the kind of brother and sister of the inversion. And with that, we reconstruct our measurements. So from those two parameters, we can reconstruct our seismic wave fields. And importantly, there we can also reconstruct all the multiple scattering, which makes the response so complex. So we try to explain all of the, tiny little diffractions, reflections in our seismic data in order to make sure that we can use it in the inversion process. So we have a closed loop process where the data comes in and we image it, we remodel the data, we match it with the input data and then we invert and then we iterate basically. So it's an inversion, we're closing the loop there. And by that you can really create high resolution images. So if this is the real image, very simplistic model of the subsurface. If you do just straightforward imaging, you get the image that you see on the right side. But if you do this iterative process, you see that you get a much higher resolution image here. You can really see the actual interfaces very clearly without all those artifacts and side lobes that you see otherwise. And that can make, of course, a difference. And another thing is, I also told you that we are going to explain all those multiple complex scattering. And if you don't do that, that scattering will end up as kind of crosstalk in your image that you don't want to see, and it kind of blurs your actual interpretation. And we've done this process on a field in the North Sea. It's a Norwegian part of the North Sea. And when you look at this area here, this is a fault block. Here, fault block, and it's covered by a strongly reflecting overburden, and that creates all kinds of extra internal scatterings, and those scattering create fake events here in your reservoir area. There, and they are like the flat events that you see here, while the fault block is a bit tilted. and those flat events kind of complicate the interpretation. And if you then do the what we call full wave field imaging process, where we include all that complex scattering, then you would see it is not strong but visible. You see that in this area here, things get a bit more clear. And the actual difference here shows what you have removed here. So this is the clutter that is interfering your interpretation and can make tiny changes that maybe have a large impact in your interpretation. So this closed loop imaging process is important. Closing the loop, I think in reservoir simulation, that's also an important term there. And at the same time, we have to also estimate this propagation speed of sound profile, because you need that to do the proper focusing of your energy. So at the same time, we create an image and we create a speed of sound map, you might say. Those are the two outputs of the process. Well, that can help you to do monitoring. Well, one of the, I would say in our community, one of the most famous monitoring exercises that has been done is the Sleipner field. So there's a field in offshore Norway. And since the 90s, they have already monitored this field because they have used it for CO2 injection. And this is the situation here. So here you see an ejector, and here you see the kind of parallel layers of the reservoir where they inject the CO2, and it kind of, it floats around in those reservoir layers there. You can see that. And interesting enough, you see clearly the response on the seismic image. So this is a vertical transect that you see here over the years. 1994 is before injection, so there was basically the bare reservoir without any gas inside. And then you can clearly see the footprint of the gas here when it was injected. So you can clearly see where the gas is being injected in this field. And this is the power, you might say, of monitoring with seismic measurements. And also you see the bottom row is basically a cross-section at a certain level through one of those areas where they have injected the gas. And you see clearly how it grows. Well, this is of course a very easy monitoring task, because gas versus non-gas is very bright. It's very bright acoustically, so you can easily see it and interpret it. However, you see one of the challenges here, if you zoom out, I take 2006 as an example here. If you zoom out there, you see very clearly the injected gas, but below there you see clutter. So this clutter here, and this is not a real gas here. This is all the multiple reflections, the complex scattering that has not been removed from the image here. So this is a simplified imaging process, and there you see this clutter here creates a lot of confusion because the gas is very strongly reflecting and thereby creating very strong multiple reflections. So this is one of the things that we would be able to resolve with our inverse method here. We did not work on this data, we don't have access to the data yet, but would be an interesting showcase to see whether we can explain all this clutter and then really reveal that below there is nothing in terms of CO2, for example, what you expect. Anyway, so this is about monitoring. Monitoring is about repeating the survey over the years, over time, and then look at, for example, difference plots, etc. So traditionally what people do is they take a lot of measurements, make the images, and then compare the images by, for example, subtracting them. What we say is, no, we have to be smarter, not just making separate images as if they are standalone and then compare them later on. No, think of them as one big group of images that belong together. And maybe you can then let them help each other. So you can do a joint inversion of all that information rather than looking at every image separately. And we did that on a realistic model. So this is a synthetic model, but it is the Grane field, which is also offshore Norway. And so we received this from Equinor, very detailed subsurface model based on a real field that they have there. And they also built a very accurate time-lapse process about extraction. And this is, of course, this is about about oil and gas extraction. So this is the actual time-lapse change. So this is the change in the reflection properties because of removing of the oil, and in the bottom is the change in the propagation speed of sound, because also if you replace the material, also the properties will change. So this is the reflection change, and this is the propagation speed of sound change because of the changes. And so there is here gas oil replacement. There's an injection there that also creates a time-lapse effect. It creates stress also in the field. And also the whole stress overburden is changing. You see this blue haze is also a change because of reducing the stress in that field. So when we just do our inversion process on one instant of the data, that's what you get here. So you get an image and a velocity profile. Okay, fair enough. And then if you subtract two subsequent images, this is what you get. And you get a kind of an idea about where are the changes in the reflectivity, and not much idea about the changes in the propagation speed of sound, because that's very detailed information that's not very accurately imprinted in your data. So if you do it one after the other, the noise of every inversion process will kind of stay there. But if you see it as one big inversion scheme, then you can get a much higher resolution result here. So then you can accurately delineate your changes in the subsurface, and also delineate, at least to some extent, the changes in the speed of sound that you have there. So this is like separate images, comparing them, and this is a joint inversion process of all your measurements. And this was a true change. And you can also go one step further and say, well, do I even have to take the time lapse, the monitoring, do I have to repeat it all the time? So do I have to do exactly the same monitoring, which is expensive? The first one is always expensive. Can we make the second one maybe cheaper? Because the first one has the big image, the second and the third can only kind of illuminate the changes. And I borrowed this idea, or well, we had the idea, but we found a similar idea into image processing. So this is low quality video images that were a bit blurred. But by having many of those frames, you can combine them if you know how those frames are basically created and how the camera was blurring the image, because the camera was moving while it was making this image. So every frame by itself has a poor quality, but the information is encoded in all the other frames. And if you kind of invert them in a smart way, you can really reveal the actual information there. So the right side image has been reconstructed from these low quality blurred images. By knowing how this process worked, and you can undo it and combine all the information. You can basically kind of interleave the information. Here, so, well, this is the thing that we also like to do in monitoring. So you start always with a big monitoring survey where you have all the measurements done, and then you do smaller scale with coarse sampling, for example, cheaper, because you don't want to repeat that all the time. Infill every year, or whatever you need, and then you can invert that simultaneously. And we did a small experiment on one of our synthetic models. So we did this process, so one big survey in the beginning, and then small repeat surveys that were very coarsely sampled. Each repeat survey was very poor quality, but by combining all that information, then the difference plot goes from this to that. So this is the difference plot if you take each of those individual poor quality images and you subtract them, and you have noise, and you subtract them, you still have noise, and that's basically what you see on the left-hand side. So all the noise you see there is the noise from the poor sampling, basically. And then on the right-hand side, you see when you combine all that information in one big inversion process. So with little information, you can still get a high-resolution result. And that's actually also driving our research. Can we do more with less data? And I think for applications like CO2 injection or hydrogen injection or storage, this is crucial. Keep it cheap and manageable and still get the information. Another thing is make use of all that complex scattering. Make use of all the complex propagation effects that are in your data. And multiple scattering is one of those examples. So you see a lot of waves travel in different paths through the subsurface, and all of them have information. And actually, Hadi, in the introduction, told about a course I was giving in 2006 in several places, and that course was about removing those multiple reflections from the data because they were considered noise. Nowadays, we say, well, no, multiple, all those extra multiple bounces, all those extra scattering information is information that you should utilize. And we did it on what we call a borehole seismic data. So you have a borehole, so the receivers are in the borehole, and the sources are at the surface, and you can do a survey like that. It's a relatively well, smaller scale survey, centered around your borehole, where is the information that you need. And typically, when you do an imaging, and you use only single scattering, so what we call primary reflection, so events that have only scattered once, then you can image only a very small area around the borehole. Because if you think of the ray paths from those surface locations, where they all bounce close to the borehole. So very poor quality information. But if you use all the multiple bounces, actually you, by that, extend your illumination. And you get an image on the right-hand side there. And it even works on field data. So this is a field data example that we did on, in a shallow water, shallow marine situation. And then you go from the image to the left to the image on the right. The same data, but a different algorithm. And we could even update the background velocity profile. Okay, but that's more of a detail. So that means that we have challenges that we would like to face, and especially in this new application area, like CO2, like hydrogen, the business model, as we call it, is quite different compared to the hydrocarbon industry, the oil and gas extraction. So it has to be done more cheaper. You have to get more information from less data. That's one of the drivers to it. So you have to be sure that you do a very dedicated design of your geometry in combination with high quality imaging algorithms. And that's the task. And we did a small experiment here, again with a borehole. So we have this 3D model here. We generated borehole data. And basically, with one borehole, we could get the image on the top right picture. The top left is the first iteration, and then when you do this closed loop process, you go to the top right, so you already expand your image quite a bit. But still, because you have information for one borehole, some areas are not well illuminated. Well, if you would have a second borehole, that one, then you see that the left side was the original from one borehole. And if you add the second borehole, then suddenly you have a much better view in this area over here. Where's my mouse here? So here. So this area here gets much better illuminated. That was completely absent here because of the ray paths will never hit this area under the right angle and get detected. So you have to be very smart, and of course when you have injectors, you can put fiber optic cables there and do seismic measurements basically even during the injection. So you don't even have to stop your operations. And if you are smart in selecting where you want to do those measurements, you can really get the maximum information out of this data. And even it helped us to get a much better propagation speed of sound profile. By using more information, you can also get a better estimate of the propagation velocities of the waves. And this is a kind of 3D image of those. And this is a plane view. So when you use only information from one well, a borehole, then you get the horizontal slice that you see on the left-hand side. And when you use two boreholes, you see the one on the top right, and you see much more detail, also delineated from your velocity profile. And the bottom one is the true one. So to conclude this presentation, so we need dedicated geometry, monitoring geometries, but you can do many more things. So we can use boreholes that are equipped with fiber optic cables, what we call DAS, distributed acoustic sensing, because that's basically, if once they are there forever, and you can use them over and over again. So I think borehole measurements could play a key role in seismic monitoring. Use all the scattering, so what we call primaries and multiples, so single scattering and multiple scattering. Well, dedicated geometries at the surface. How do you put your sources at the surface to get the right illumination? Well, also, can we combine old surface seismic data with new borehole seismic data? So that's another kind of combination that you could utilize here. So the first survey doesn't have to be a borehole survey, it could be the traditional surface survey. And we can use different kind of measurements, passive measurements, and for example also use shear waves at the surface waves, rather than pressure waves that go into the subsurface. Well, those two topics will be talked about by Dean tomorrow, so you'll hear more about that part. And then finally, I talked only about seismic, but there are more physical measurements that we can do. So my personal expertise is more seismic, but there are other experts in Delft and around the world, of course, that can help in maybe combining seismic with EM or with gravity or potential measurements. So there is much more that we can do there to get the best information that we would like to achieve in the subsurface, in our reservoir area. Well, the last thing I would like to say is that we are currently applying for a project together with Hadi, and hopefully we can get 1 or 2 PhD students that are going to investigate what can we do, especially for the hydrogen storage. So what need to be seen, and what can seismic or other geophysical methods do for that. So that will be very exciting. Well, with that, I would like to thank you for your attention.
Thanks a lot. How many conferences have you been that geophysicists have given talk? I mean, it's Interpor, no geophysicists, so welcome to our community. You know?
Yeah, thanks. Yeah, it's my pleasure.
I have a really technical question, and even though this isn't my area, I think I've learned enough from you to ask this question. So I think what you're detecting is edges that are where there are differences in density.
Or properties in general, yeah. So it could be density or well, bulk modulus, whatever.
So, okay, that is my question. That you're looking for edge. You see edges, but you also see the bulk prop. So here's my question: the gas phase, when these waves are passing through a fluid, can it detect different fluids?
Yeah,
like,
so actually I had it...
You know, so what I'm getting at is, can you tell if the hydrogen has become half methane from a biological process? Can you tell the composition?
True. No, so if we talk about the... let me go back to the slide about Sleipner, because I like that slide a lot, because it really shows the situation that we are at. So this is easy, because this is between gas and non-gas, and that's a huge difference in properties. So the question is, how big are those properties? So density and bulk modulus, basically, those are the 2 properties. So if there and then there's a combination. The speed of sound is the ratio of the 2 with the square root. So if there are differences that are maybe a few percent or something like that, then we could possibly detect it. And it might also be that it's not only the pure detection, so it's about amplitudes, first of all, so the brightness. The second thing that you can use is that if waves reflect from this side or under an angle, there is already a difference in the reflectivity, and that's another discriminator that we have. So also in the typical oil and gas scene, what they call AVO, amplitude versus offset, but it basically means reflectivity as a function of angle of incidence. That's a very important parameter, because even if in a normal incidence they are almost the same, then under a certain angle they show slightly different properties, and if you then keep track of that, then you can still make a distinction there. So there is an extra dimension that we would have, which is the angle of incidence, that could highlight small differences, but it has to be differences in the first place. How big are the differences? That's my question to you, or maybe to the audience. How big are those differences?
You're working on it.
Yeah, and that's probably also one of the things we want to discover in this this project, because that's a challenge. I mean, when they replace oil by water, for example, also that is not too different, but it's large enough. I think it's like 5% or so in properties difference, and they can detect that. But the gas and gas, okay.
Speed of sound.
That will be one of the big challenges I feel about this hydrogen storage problem. Yeah.
For example, a CO2.
Catherine, people should hear you.
Let me follow up my question. A CO2 bubble can be far more dense than a hydrogen bubble at the exact same depth, and so those you should be able to see that.
Yeah, that would be easy.
Okay.
Yeah, that would be easier. Yeah, I think so.
Yeah. The contrast is higher.
Yeah.
More questions? We have one.
So I think the main answer is we need a few percent at least of difference in properties. Then I think we have a chance. If it's promils, then okay, then it's difficult. Then it's in the noise. But a few percents of differences in density or bulk modulus, that could be helpful enough. Yeah, could be good enough. Yeah.
Okay. Okay, Guillermo Giacomi from UPN Madrid. Okay, my background is mainly seismic processing and interpretation, so I'm quite a fan of all this. What I want you to ask, for the last 5 years of my life, I have been working in quantity interpretation. Are you considering to also work more on the petrophysical part, meaning incorporating well data to your seismic?
Yeah, true.
Because coming back what Susan asked you, yes, there is a relationship between BP, BS, density, and seismic data. That's the way you create synthetic data. But you can also use the information you have from well logs, which is the hard data you have.
Yeah, no, so I fully agree. So when I talked about estimating a velocity profile and estimating a reflectivity image, that's only part of the story. That's you might say that's the context. But then the next step is really to dive into that and say, well, okay, in this pixel here, what is there? So if you look at one pixel of the image, when you zoom in there, then we can expound on that and then talk about, for example, angle-dependent reflection properties. And that is a key information that can be combined with the actual rock properties that you would have. First of all, elastic properties, so the bulk modulus, density, etc. But finally, you would like to link it to like rock type or lithotype, etc. And to make that step, you really need borehole information. The well log information is crucial there. And so you might say the geophysical and petrophysical context is helping you there because it's an ill-posed problem. So the only way you can solve that is by including and say, well, in this area we only expect this range of parameters because that's what we see in the well log, for example. So we first indicate which layers there are and then what would you expect in each of those layers. And that's prior information that is crucial. Otherwise, your output will probably not be so successful. Yeah. So true. And one of the things we also look at is how machine learning could help you there. For example, so machine learning could discover this kind of statistics, stochastics, whatever that's behind this, and help you basically in this identification. Yeah. No, it's a key step, especially when the differences are so small. If you think of only a few percent, you need any type of information, also where it is in your image, what is the surrounding area, etc. All that context is important to say something about that pixel. Yeah,
yeah, Bart Langman Shell. So my area is not seismic, but I learned a lot. Thanks for that. But I probably got this wrong. But I would like you to ask to clarify that for me. You mentioned that the whole challenge there for you folks is also less data. With less data, having a better image. But especially with the comparison that you did with the blurred picture, I'm fully convinced about the better picture. I cannot yet see the less data component here, if you understand what I mean.
Yes,
so I see that you have the same data, but you're simply very much better in getting proper data out of that, but not necessarily less data.
Yeah, so of course we want more data. In principle, it's not our goal in life to have less data, but of course we have to be practical and say, well, if you want to use the seismic method, it has to be cheap enough to make it affordable in this kind of situations. We're not in the wealthy oil and gas situation where we can throw millions of channels to it and then do large surveys and get whatever you want. So you have to be very kind of smart in saying, well, okay, if we have this amount of channels, how can we distribute them optimally so that we can really get the information that we want? And also be smart in using all the information. So what you see there, this clutter that you see below the strong reflecting horizons, actually that is considered to be noise, but you could also say it's signal, because it says something about those levels that are above it, because there are multiple reflections. So what we try to do is basically get that information, map it back to where it came from, and get even higher resolution there. So that is being smart in the application. It's the same data, but being smart in the application. And on top of that, you could say, well, if I make use of that, so I have less noise in my data, maybe I can also live with less data. And then the third thing is, when you do time-lapse measurements, 4D measurements, then you can also use them smartly together so that they reinforce each other. So you might say 3 things that help you to get more out of whatever data you're measuring.
What do you think to using fiber optic to monitoring the reservoir?
So, sorry, can you repeat the...
What do you think to use fiber optic?
Fiber optic?
Yes.
So what I mentioned, the fiber optic cables, the DAS cables. Yes, so these DAS cables are nowadays, well, they're used for many different purposes. They're already in your borehole for temperature and all kinds of other parameters. But in the last 5-6 years, they have been, well, maybe even 10 years, I would say. There's a huge revival, or not a revival, but a vival, well, what you call it. But it has become apparent that you can also use them for seismic measurements. Although nowadays they have specifically created fiber optic cables, especially for that purpose, because they make them a bit rough on the inside, so there is more scattering, and they have a higher signal-to-noise ratio. But the good thing about this fiber optic cable is you can put them throughout the whole borehole, so you would have free access to measurements all the time over the whole borehole. And in the old days, what we have to do is we have to put a tool in there with geophones, and they have to sing them down step by step, and repeating the measurements is a very expensive process. So by having this installed fiber optic cable, the only thing you need to do is put seismic sources at the surface. That's the only thing you have to do. And then you can just listen to the signals that are received by that cable. And in that way, you can have relatively cheap, and even without disturbing the production process or the injection process or whatever, because you can do it separately from each other. And you can have data anytime you want. So these fiber optic cables are a huge enabler, I would say, for monitoring in this kind of situations. Especially if you have multiple boreholes, which you probably have. So you can put every borehole one of those fiber optic cables, and then once every time you need it, you can go there with a seismic source and try to shoot it over there.
We have some questions online as well. One is about just the slide that you're showing. It shows that you have done also survey before injection or before the process as well, and how crucial it is to do it before we start to do storage, a survey.
Yeah, I think that well, in this
sharp audience.
Well, I'm not sure whether it was that crucial for this situation. It was just there anyway because they had the data. So I'm not sure whether it was intentional to have it there as a starting point. But at least what I would like to have is a good data set in the beginning. It doesn't have to be at the very start. So at the very first stage of your process, have a good data set, well sampled, and then you can subsample from there and make things cheaper.
So Eric, another question is about, we spoke about the space resolution. Is about now when we do cyclic storage, seasonal or weekly, it's about now time. And would you also comment about how frequent we should do these surveys, or how about if we are injecting and also producing as well, and injecting again and producing again? So it's going to be a bit more dynamic than this.
Yeah, so of course, the answer to that is I don't know yet. I would like to figure that out. So I only have some intuition here. And the intuition is, what is the question you want to answer? So I can imagine one question you want to answer is everything in place? Is it leaking? Okay, so that's something that can be done maybe at a rougher scale, because that's not so much related to cyclic processing, because if it starts leaking, it will continue to leak anyway. So the leaking is something that you would like to monitor maybe every half year or something like that, I can imagine. But if you want to, well, if it's cyclic in like a 24-hour or maybe a yearly kind of, well, I can imagine that you do 2 times a year, something like that. But it depends a bit on the question.
I see.
Maybe that's what I would like to hear from you. What is the question that is need to be answered?
Absolutely. That's why we should work to get them more. I mean,
yeah.
Yannick Garo from Geostocks, and you were mentioning monitoring and leaking. What is the kind of resolution you can expect? 1 million ton, 1,000 ton, 100 ton, 1 ton?
Well, I can only tell something about scale, about meters. So maybe you can translate that. But I would say typical resolution here. So if you, I think you would be able to see leakage, because leakage is relatively clear. However, if it's too small, you don't see it. So it has to be already expanded over maybe a few meters or 10 meters width before you start seeing it with seismic. That's my guess here. That's also another thing that we have to figure out. How big is the leakage, and is it already too late? Of course, when there is a leak of a few centimeters, you will not see it, because the seismic wavelength is almost half this room or something like that. However, small heterogeneities can be spotted in an early stage. So one kind of anomalous pixel, if you might say so, can be spotted in a way. And those pixels are about maybe whatever 10, 20 meters or so. So that's the kind of size.
Very last.
Okay.
Let's discuss that. Very last question. We need to finish at 6. Please go ahead.
Thank you. Hein van Gens, Staatstoezicht op de mijnen. As a regulator, I am scratching my head a little bit about sending seismic trucks or vibro-seis or dynamite crews into a built environment twice a year. I understand that this offshore, this will be a lot simpler. But what are your feelings about using passive sources, and then specifically on the Netherlands, and for example also induced seismicity?
Yeah, true. So that's so that could be another source of energy here that you can use. Actually, Dejan, tomorrow he was already raising his hand. Okay, the question might be answered tomorrow. So I think that's a very viable option. So if it allows you to do active seismic, of course nothing beats the quality of active seismic, because the signal-to-noise ratio is quite good and you have more control. But if you are limited by what you're saying is, passive seismic is a very good alternative, and especially on land where you don't have these options to do active seismic, I would really encourage also investigation in that area. Yeah, true.
We need to finish at 6, so we have a full program tomorrow as well. Let's thank Eric once more for this excellent talk.